Good. All right. So can I? Because it's no time.
Yes.
It's good. So now it's okay, or?
Yes.
All right. Good. Thanks so much, and then thank you for your patience for usual technical problem. Yeah, it sometimes happens. Okay. So let me go back, and then thank you again for kind introduction, and then I'm now going to talk about. Present my work, boundary STL checking for hybrid systems. And probably, first of all, I have to thank to the organizer, Peter and Cyril, to give me opportunity to present my work here, and then it's quite an honor. All right, because I have no time, so yeah. Okay, so probably many of you already know, but it's quite related. I just briefly summarize background on temporal logic. Yeah, usually, temporal logic specify properties for computation of discrete systems, right? And then, linear temporal logic actually is quite close. Huge relationship is a signal temporal logic. It's properties of a sequence of states. And then this is the one example. Whenever x is less than 1, the value of y will eventually become 0. Can be explained in LTL using famous square and diamond operator. Right? And then I use this formula for STL as well. And of course, more checking ask whether all possible behavior of the system satisfy this temporal logic formula. This is a typical discrete system situation, but for hybrid system, which combine both discrete and continuous behavior. So the discrete part could be just the usual program or transit system, and continuous part would be represented some continuous function or ordinary differential equations and so on. And then, of course, already Peter introduced cyber-physical system, one of the example of hybrid systems. Yeah, and then here, if we consider precisely the behavior, then actually you have to consider these continuous signals, because there is, of course, discrete states, but many important properties are given by changes of these continuous variables over time, like position or velocity, something like that. Therefore, you have to consider that. And then signal temporal logic is a property to specify properties of those continuous real-valued signals. And as a simple example, suppose you have some two continuous variables, x0 and x1, and then suppose they change over time like that. And they are not linear because there's a slight curve over there, because it's generated by our tool, but yeah, looks like too straight, but it's not actually. And then probably you can consider some time-related property like that. From 2 to 4 seconds, whenever the value of x0, x minus x1 is greater than 4, then after 3 seconds, before 10 seconds from that point, the value will be less than minus 3, something like that. Yeah, although in natural language it's slightly confusing, but if we written in temporal logic, which is quite similar to the one for LTL I just mentioned, but you may notice that there is some time bound annotates the temporal operator. So, for example, for this square operator, this means that from 2 to 4 time unit, the formula inside this parenthesis must hold, and then this diamond say that from time 3 to 10, at some point, this proportion hold. Therefore, by combination, at any point from 2 to 4 time points, all right, this will hold, and this means that during this point, whenever this hold, then from that point, from 3 to 10 time unit, for some position, some moments, this condition hold. All right, so slightly a little bit complex, but it's quite similar to LTL in some sense, because the only difference is that this interval gives some restriction. about the moment of events. Yeah, and then this actually extends the syntax of LTL with local timing constraints, like interval, and then, as mentioned by Peter, is syntactically identical to metric temporal logic for real-time systems, but semantically it's different because it involves some continuous signals and so on. Okay, so and then this STL proposed like a 2005 around there, and then after that it's widely used for monitoring and falsification. That means given simulation or testing, which will generate some concrete signals, the monitoring check whether that generated signal satisfy this STL requirements or not, and falsification is to generate or synthesize counterexample by somehow various simulation and then optimization techniques. And then they turns out to be very effective for analyze concrete samples of signals to find the counterexamples. Yeah, and then there's so many different techniques and tools for that purpose. But as usual, although they are very useful to find some errors, but they cannot guarantee correctness. And also, it's slightly difficult to find some subtle errors using those techniques. Yeah, just some typical situation. And then there are also some verification technique or model checking technique of hybrid system exist. It's also since almost mid-90, more than 30 years ago. There, the hybrid system specified as some mathematical notation, and from there, it's possible to symbolically analyze all possible behaviors. But those techniques mainly focus on invariant and reachability properties, or their slight variation. Yeah, so there's so many techniques and tools for analyzing invariant and reachability property to guarantee correctness for hybrid systems. And then by slightly modifying that or generalizing that, it's also possible to check simple, very specific form of STL property, like that, given initial condition, whether some invariant hold like that. But STL model checking for general STL property is previously not much studied. Probably there are several reasons. One is that even for invariant and reachability properties, the speed performance is quite slow, yeah, for obvious reason, because have to consider infinitely many signals and so on. So people focus on improving the performance of this reachability analysis techniques for many years. Okay, probably it's a main reason. And also for general STL property, typical technique used for metric temporal logic is not that effective. Therefore, yeah, it's good to, of course, develop some technique to verify general STL properties of hybrid system, and then that's the motivation of our work.
Can you ask questions?
Sure.
In your example, with just two values, we could do predicates.
I'm sorry, can you please
In your example, you could do a predicate abstraction if it's just two signals and inequalities. And then, to me, it feels it would be fairly efficient, but maybe in more complex cases, this wouldn't work anymore. What is the reason?
Predicate abstraction technique? Or?
Yes, for example, there are certain intervals where the difference is greater than 4. So you could have a Boolean and track just that and the interval, and then you could, in this case, maybe reduce it to regular.
So it's slightly more complicated, because here actually the meaning is that, for example, for any moment like that, say time 2.1, if this hold, then from time 3.1 to 10.1 this hold, and then say 2.2, 3.2 to 10.2 this whole and so on. So therefore, it's not easy or immediate to just split the interval.
Okay, because of the nesting. Okay,
Yeah,
thanks.
because of nesting. Okay, so actually it's a very good question because I mentioned that Moore checking for invariant and reachability and some variation exist, and then actually when the interval can be specifically separated, then that's actually easier, and then there's several techniques for encoding that as hybrid automaton exist actually. But actually, that might be possible for a general STL property as well, but it's not been developed. And then a part of this technique I mentioned today can be also applied to generate some hybrid automata as well. Of course, it's out of the scope of this talk. Actually, it's my future talk. Yeah, so because of this arbitrary nesting of the STL formula, it's not that clear how to do that systemically. Yeah, although it's possible, but unless not developed previously. Okay, so any other question? All right.
Short question. Did I get that right?
And this also applies to metric temporal logic as well. So, because
Sorry, a quick question. Did I get it right? Is the intervals, are they all with respect to the global time point 0, or are the intervals to be interpreted in a relative manner?
it's actually a relative manner.
Okay,
So top
cool.
one is with respect to 0 typically, and then the nested one with respect to the just above one, and so on.
Very good. Thank you.
All right. Okay. Yeah, and then of course for developing this STL technique, there are some typical challenges. First of all, STL checking is generally undecidable. That's kind of obvious because even invariant property is generally undecidable for some general hybrid systems. Of course, for very strict hybrid system, that can be decided like a timed automata case. Timed automata can be one of the hybrid system as well. Yeah, right. But it's generally undecidable. And second one is that boundary Moore checking of STL is also difficult because boundary signal can be any arbitrary complex. For example, given any fixed duration of interval, we can give arbitrary complex behavior. For example, by increase this number 10 to 100 or 1,000, we can have very complex behavior, arbitrary complex behavior. Okay.
So just to be sure, because maybe. So signal, you said infinite number of signals, but isn't that? I mean, isn't this whole thing one signal? I mean, I mean, so a trace of X is one signal, right?
Oh, this is to illustrate purpose.
Yeah,
It's typically given as ordinary differential equation with different initial value.
Yeah.
So basically, in practice, some parameter of initial value will be different. Therefore, given arbitrary initial value for a specific duration of a signal.
Okay, so it's, but in general, I mean, signals are sort of deterministic and so on, right? So
if
once you start,
once you started. But for specific discrete state, discrete state, the number of initial value for that state would be arbitrary. So, and also it's possible to allow arbitrary control input from outside as well. So in that case, the dynamics itself could be infinitary as well. Yeah, and then in this talk, I'm not talk much detail, but robustness of STL checking is even more challenging because for discontinuous signal, if there's small error in sensors and actuator, then the truth can be just changed, right? So by giving very slight difference, verified property could be violated and so on. That's not desirable. Therefore, some kind of robustness is important, and then how to deal with that for verification is also important. Okay, so basically, our approach to address those general challenges is to perform bounded monad checking of STL properties for hybrid system using SMT solving techniques.
So, if you can go back to previous slide, so you said this arbitrary complexity of the signal, right? But I thought you made it discrete, but once you make the thing discrete, that signal can only take same value for like 0.1 second. Does this result still hold about undecidability?
So actually, it's related to previous question, right? So
Yeah, okay.
if the given state, because there could be many different discrete state, if the initial value for that state is fixed, then usually the signal is deterministic, but the initial value could be in some interval as well. So basically, infinitely many initial value for certain discrete state. Yeah.
So if
For
you
example,
also,
for this example, initial value of x, y, and theta could be some interval for the first mode, and then when changed to different mode, there could be another interval, and so on. Therefore, there could be arbitrary complex behavior. That's a typical. And then another thing is that actually continuous DMS can have also arbitrary control inputs from outside as well. Although the control input itself is assumed to be piecewise linear, though. Therefore, could be
just to follow up, like, so if we limit the value of the signal to be discrete, like it can only be some value, and it has to be constant for like every small duration, let's say epsilon, then you have the whole system to be
Yeah,
completely
so
discrete, and then everything is like can be reduced to LTL, I guess, right?
Actually, there's a dedicated technique called STL monitoring. So STL monitoring technique try to efficiently compute given concrete signal, initially fixed and then all the behavior fixed, to efficiently compute the truth of given signal with respect to STL formula. Yeah, there's an extensive study about STL monitoring.
Thank you.
And it could be very useful for testing, but because yeah, right. But because you have to, it just rely on some sampling of finite number of values, therefore cannot guarantee correctness. All right. Okay. And then the goal is reputation complete for boundary signal. So there exists some previous technique that insists STL monitoring, STL monitoring checking. But the problem is that it's mostly about sampling as well. So typically, does not say correctness is guaranteed up to certain bound. So therefore, I wanna have some good property for bounded LTL monitoring checking. So for bounded LTL monitoring checking, you can say that up to some number of discrete transition, the correctness can be guaranteed. Then question is, how can you do that? And then also robustness. Turns out to be actually quite simple though, but it's also important to define, provide some robustness up to some threshold or error bound. And finally, you want to develop tool, STLmc, actually developed, of course, that can deal with general STL formulas. All right, so let me briefly overview some detail again. Okay, so basically I mentioned that you want to develop some bounded monad checking technique for STL, just like there exists bounded monad checking technique for LTL. Of course, for LTL case, typically you can do that using SAT solving, but STL, you want to do that using SMT solving, together with some specialized solver to support nonlinear dynamics or even ordinary differential equations. So for LTL case, so we can reduce the satisfiability, the monad checking problem to satisfiability of proportional logic. And then the idea is many of you already know as follows. First, the computation of a system up to certain bound number of transition can be encoded as a SAT formula, and at the same time, the existence of LTL counterexample up to certain bound can be expressed as a proportional logic formula. So, and then that can be done by some famous equivalence. For example, for always phi formula, basically we can say the first state is satisfied and second state is satisfied and so on. And then for eventually phi formula, it's either satisfied in the first state or satisfied in second state or and so on, right? And then for a more complex formula like until formula, similar rule can be defined. Therefore, by using the kind of equivalence or translation, you can easily encode LTL formula as SAT formula, which is proposed in late 90s by several researchers. Okay, then for boundary model checking of STL, then how can you do that? So as you mentioned, we want to reduce the satisfiability to a SMT problem or first order logic problem. And then, okay, similarly, we need two things. First, we have to encode the behavior of a hybrid system up to time bound. And that's already done by another work, because I mentioned that model checking technique for invariant and reachability are studied extensively for hybrid system. And then this is exactly the related to the technique for model checking invariant and reachability problem. So this is good. But problem is that for second one, encode the existence of STL counterexample up to some bound. And then some immediate difficulty is that there's uncountable number of states over continuous time with nesting. There's already asked several times by in the question, and then this could be arbitrary nesting of different formulas and so on. And then the computation is not really bounded. And for real-time system, typically we assume non-zero behavior, right? So that the change of state should be only a finite number of times and so on. But by definition here, signal temporal logic, the change of states could be infinitary. So therefore, we cannot assume non-zeroness of real-time system and so on. And then actually here, the solution is quite simple, because we can just consider similar properties non-zeroness of real-time system. But slight difference is that in the real-time system, non-zeroness means that the change of state itself is finitary. But here, we require that the change of the truth value of subformula change finite times within a fixed bound. So it's a kind of non-zeroness condition with respect to subformulas. So it's a when some truth value of formula change, we call as a variable point. So just assume that. So therefore, we want to model check STL formula with respect to finite number of variable points. Therefore, the bound parameter would be this variable points. Okay, so it's a simple idea. And then we can freely limit model checking computation involving continuous behavior, like the previous example of this arbitrary complex signal. The number of, if we limit the computation up to number of variable points, then it can effectively bound it. All right, so just to give us some shortcut notation or terminology, I say some STL formula is stable in interval if the truth of the formula does not change within the interval. All right. So basically here, if those time points are variable points, then truth of the signal with respect to formula in each interval in the middle, the STL formula is stable. All right. Okay. So the first idea is just to perform that kind of technique. And this is just a brief overview of how to encode hybrid system itself in SMT. I mentioned these are already studied for a long time. So basically, in a hybrid system, we assume that the state is given by some discrete state, say Q, and some real valued vector. And then the encoding defines some initial condition where the initial state must satisfy. And of course, this is just condition, so therefore there might be infinite number of concrete states that satisfy this initial condition. And then the continuous change could be defined as symbolically some SNT formula written this flow. That means given some initial value for duration t0, the resulting state will be this v0 t. Okay, so this can involve some arbitrary continuous function or ordinary differentiation, solutions of ordinary differentiation and so on. And then you can typical discrete jump from some state to another state. All right, so basically by conjunction of this initial flow jump, we already describe or encode the behavior of hybrid system in one step. And then by repeatedly doing that, we can easily encode the reachability problem or invariant problem of hybrid system in SMT. Okay, so that's somehow easy and well understood. So actually we wanna use that for system representation or system encoding. And of course the only problem now is how to encode the property part. Okay, so basically in order to encode the property, we just assume given STL formula and some variable point bound. And then as I mentioned that basically we just want that truth value of each sub-formula is stable. All right. So basically there we provide two things for our encoding. First, we have some SMT variables to denote the times. Right. For example, if there's a k variable points bound, then we can provide a k SMT variable to denote each variable point in the position, right? And then those time points will provide some interval for 0 and open interval 0 to tau 1, and tau 1 to tau 2, and so on. So this graph show some potential instantiation. Okay, and then for now each subformula, you wanna provide some truth value. Okay, so for example, for this formula, there's three other subformulas. Then we just assign a truth value as a Boolean variable. Okay, so in our SMT encoding, so basically we have a SMT variable for each variable point, and then truth value for every subformula. Okay, so those are all the variables needed actually for encoding behavior of STL property, right?
Hi, I think I missed it, but is this partition, doesn't it depend on the initial condition or something? Like, is it unique for a given?
Oh, actually I say there's SMT variables. So those are variables for SMT encoding. So basically,
you're not generating the partition. You just it's some symbolic like partition. For
symbolic partition exactly.
Thanks.
Yeah, because just assigning those variables are not enough, of course. And so we need extra condition. That's actually SMT formula, right? To exactly define symmetric relationship between those SMT variables. Okay. Yep.
You can take questions also. So I think this whole. Okay. I mean, so maybe I missed something, but this whole encoding, of course, given a variable point bound k.
Yeah, exactly.
Where does that k come from?
From user.
From user.
Yeah.
Okay, so it comes from user. Okay, so that's.
Good question. Thank you.
That's the hack
Thank you for
here.
clarification. So basically, just like typical LTL model checking, where the user must provide bound. LTL boundary model checking, the user provide the bound, right? So actually here, the user provide also this variable point bound. Yeah, because even having the bound from the user, we can increment the bound from 10, 20, and so on. So that's what's possible. So there are two ways. Either the tool automatically decide by heuristic some initial bound and then increment the bounds, or user can just give a hard bound. Both are possible. All right, it's just a typical bounded model checking scenario. And then there, for STL encoding, we need several symbolic variables or SMT variables to describe time points and then truth of each subformula. So therefore, if we can define some SMT formula or first logic formula to exactly capture the relationship so that satisfiability of this formula, that means that the question of finding some assignment to those variables is equivalent to STL matching problem, then we are done, right? So then the question is how can we find some encoding to make the satisfying assignment for this variable is exactly equivalent to bounded model checking, bounded STL model checking problem. Okay. Yeah, but of course there are some challenges you have to consider. But by the way, any question? So I think that there's some higher level idea I try to make. So yeah, slightly detailed, but for the algorithm level or encoding level, this is the highest level of explanation I can have. But if there's unclear things, then feel free to ask me. Is it good? Right? Thank you. So one thing is that for LTL, actually it's easy to identify some subformula that only depends on specific part of system. Right? In the LTL, there's a next operator. So next operator say nth. If there's a two next operator, then it denotes second state or third state or three next operator and so on, right? So basically in the LTL, it's kind of trivial that each subformula related to specific state. But in STL, it's not actually, because of this time interval. It's not clear how to have some kind of semantic fragment of each subformula for each interval. So, for example, consider this formula. Then for the second interval, which part of the formula related to that? Yeah. So, right. It's not clear because of this overlapping of interval. I can give you some example later. And the second one is that basically the size of encoding depends on number of these time variables, right? And then, of course, having the minimum number of those position time points, say exact number of variable points, that might be ideal, but it's not actually easy. Therefore, typically we need more time variable. It's still stable, but it's not optimal. Then the question is how can you reduce the number, right? Because the redundant time points can make the analysis very slow. Yeah, as you can expect. Yeah, so as you can expect, STL model checking in our approach is by default as slow as existing invariant model checking, because we use invariant model checking subroutine. And I mentioned that because invariant model checking is already slow, therefore people focus on that, right? Therefore, it's a good idea to at least avoid some redundant computation. Okay, so each of these idea or difficulty can be addressed by the technique I mentioned now. So for the first question, we consider some syntactic separation. It's actually typical in LTL. So LTL naturally supports syntactic separation, extensively studied in 70s by several famous Kemp theorem and so on. So it's basically we want to obtain some equivalent formula where the satisfaction of each subformula all depends on specific time interval. For LTL, depends on specific state, but here specific time interval. Right. So for LTL, I state, but STL for specific time interval. But that's by default non-trivial. For example, consider this example. Actually, I already mentioned this several times thanks to several questions, but now I graphically show the example. So this means that for any time points between 0 and 2, say u, the interval from u plus 1 to u plus 3, the q must hold at some point, right? So basically, for any u, there's a u plus 1 to u plus 3. That's actually related to a serious question, right? Because of nesting. So therefore, no formula of this form. So even if we manipulate those formula using standard STL syntax, but no formula of this form can exactly capture some interval. So probably you need slightly more, right? So for the LTL, because of its simplicity, we can exactly use the same syntax for syntax separation. But for STL, separation is possible, but it's not disjoint. Okay, so it's a more concrete example. Suppose that this formula again. Now suppose that we want to separate the formula, top formula only at time 2. Okay, then actually I mentioned that separation can be done. So actually in this case can be done very easily, right? So from 1.1 to 2, this hold, because we want to separate at 2. And then exactly 2, this hold, and from 2 to 5, this hold, right? So looks okay, looks good. The problem is that the first part actually depends on interval 1 to 2 because this part, x greater than 0, corresponds to this interval. And then this interval corresponds to sum of this one and this, therefore correspond to 2 to 5. Okay? And similarly for the second one, this truth depends on 2 because x greater than 0 depends on 2. And then 3 to 5 because, you know, this guy depends on 3 to 5, and so on. And therefore, each part has some overlapping. So basically, this separation, this natural separation, cannot provide this total independence. Yeah, might be possible to encode to provide SMT encoding without that disjointedness. That might be possible, but actually our idea is to have some same situation as LTL. And therefore, if we allow total differentiation or separation, then SMT encoding might be very easy. Therefore, the question is how can you do that? So that actually the idea is that we don't need to stick with STL syntax because this STL separation can be only done inside encoding process. Therefore, of course, for the user, want to have the exact representation, but for the algorithm, we don't need that. Therefore, actually, just consider slight variation, STL with global time. Okay, so related to another question, right? Because yeah, you just want to add global time as well. So then truth of self formula become vacuous outside of the global formula. Therefore, you can naturally distinguish or make independence all the sub-formula to specific interval. That's very easy now, right? For example, by adding this global interval, we say we put global interval as a superscript. Then means that this operator say the previous meaning of the usual STL operator plus only consider this global interval. Okay. So therefore, it's trivially the truth only depends on the interval. And then the syntax separation can be much easier because we only need to put some separate interval at the global level, and then we can just leave the local interval the same. Okay. All right. So looks like very simple, but actually this work now involves several other definitions of semantics and so on, so slightly complex. But I skip the detail, but I just mentioned that we are able to define the semantics of that and then some separation rules. Okay.
So these global time intervals, do they split up into more and more intervals with each level of nesting in the formula? or may they, in some cases, split up?
Okay, probably. Actually, there's an example in the next slide, but for each level, okay, we only need the same thing. And then by using famous formula sharing technique, the size of the formula separation result can be polynomial. Without sharing exponential, but sharing. It's just like the LTL case, because for LTL case, each subformula separate to specific number. So it's the text size increase exponentially, but internal representation you're sharing is polynomial, right?
So I'm more confused about the meaning of this global interval, because of what it seems like that it says that if P is true from 0 to 2, then eventually Q has to be true between 1 and 3. And then you put this constraint of 0 to 2 on the subformula. Now,
Okay. Yeah, so it's actually in the natural language, it's slightly unclear. And then, of course, it's clear if I show concrete definition. But it's complex. But the idea is simple. So basically, you can just assume that existing semantics is just same as existing meaning, except just make vectors outside of given global interval.
so I can just take intersection of this and say it's basically 1 to 2 then for Q.
Yes, basically, you can consider, okay, if as a semantics have stereo signals, okay, then without global interval, we can consider some stereo signals satisfying this formula. All right, and then that involves some interval from 0 to 5, for example, right? From 0 to 5. So signal of length 5 will be related. Okay, we just ignore 3 to 5 there. So only consider 0 to 2. So just kind of the given stereo signal is some discarding all other part of that except global interval.
But this is not then directly equivalent to the original formula.
Oh yeah, it's equivalent to original. Ah, okay, this one. Okay, not equivalent of course.
Yeah, okay.
Yeah.
Okay, so you do it for multiple global intervals. Okay.
Okay, so as I show some example, probably this example should appear earlier. So consider this formula. Okay, then you can easily separate as you can just imagine at the top level you can separate at time 2 less than 2 equal to greater than 2, and now equivalent, right? Now equivalent, and then the second level you have to also separate less than 2 equal to greater than 2. Okay, looks like exponential growth, but you know this formula can be shared. Therefore, as usual for typical LTL separation, that's show that it's easy to say permanent. The size is a polynomial with subformula sharing. Okay, because the size is 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all, right? Because all subformula shared. All right. Okay, so now we can understand what will be separation. With the global interval is very simple, right? And then there's some result now. The detail will not be shown in this talk. Okay, given separated STL GT formula, is now quite straightforward to generate eccentric formula where the satisfiability is preserved. So it's basically given symbolic variables. We can obtain some syntactic separation. We are separated at each time point. For example, for 2, just like that, right? But for some symbolic variable tau 1, you can have a similar separation, right? And then you can obtain a first logic formula that capture the constraint over eccentric variable over this time variable, and then the variable assigned to each subformula. Okay. And then some theorem is that if this formula is satisfiable, if and only if the phi is satisfiable by signal with m most, not exactly, sorry, but m most k variable points. But there's some assumption. Each subformula of phi is stable in each interval of the corresponding partition, so that each subformula does not, truth of each subformula should not change, right? And of course, in this purple work, we also provide some basic result for encoding this part using existing technique that I'll explain right now. But before going to that, let me know if you have any question. By the way, how many Is it here?
You have like 16 minutes left.
1 hour?
16 minutes left.
Oh, 16. Oh, okay. Less than 20 minutes?
Yeah.
Oh, okay. I will repeat, sorry.
Because it's 1 hour, right? So
Oh, I see.
yeah.
Okay, already. Uh-huh. All right.
Very simple question, but just to make sure that I got it right, is the ability, the use of variable points instead of time, it makes you able to capture infinitely long trajectories, right?
Yes or no?
If infinitely many variable points are stable, right?
So it's actually yes or no. The yes
Or at
means
least one,
that
I mean, yeah.
if the time bound is just infinite, it's still possible to have only finite number of variable points. And
yeah.
for certain case, like that, just a typical SMT solver case, we can deal with that.
So if you have one variable point which remains stable for the formula, then you capture an infinite time trajectory, right?
Yeah, for a certain case,
yeah, yeah.
not all, because it depends on underlying solver.
Sure. Yeah.
Yeah,
Okay.
But for many continuous solver, especially for numerical solver, the bound must be given. Therefore, for some case like encoded using polynomial SMT solver, like YICE 2 or G3, for other case, in practice, the bound should be given. Yeah.
Just a very quick question. Why did you choose 2 in that when you were doing the global interval? Why? How did you come up to know that 2 has to be the separating point?
Here, the separating point is just symbolic variable. In the example, just arbitrary. Yeah, just arbitrary. Yeah. Okay, and the problem is slightly fast, but the idea here is simple. So now actually we wanna accomplish this condition. So basically, given time points, we have some partition of intervals, right? It's alternation of the point and open interval. We say some formula is fully stable if each subformula of this formula is stable in each interval in the partition. Okay. Then of course the problem is that we want to have that only proposition is stable in a partition because that can be encoded using typical reachability invariant solver, invariant logic technique. So from this condition, we want to obtain some refinement of partition. For example, refinement is a more the finer partition, typically having more endpoints, right? Here, Q is refinement of P. So we want to build a refinement of original partition P, where now this phi is fully stable. So not only stable for this proposition, we want to stable for every subformula. And then the question is, of course, is does this exist? The question is yes, it actually exists for a long time because even the early work of metric temporal logic by Allo and Hetzinger, it's well known that it's possible to develop a fully stable refinement because it's somehow foundational assumption of timed automata based model checking over metric temporal logic. So the idea is very simple. So given some formula, for example, with endpoint to A and B, and if the subformula phi, immediate subformula phi is stable in this partition for these time points, then for considering additional points like that, original P plus this T minus the left-hand point, union T minus right-hand point. So it's provide more finer partition. By considering these time points, then this is stable. So this is already well-known this work. And actually in the popular work, we use this result to give reputation complete model checking algorithm. But of course here is some problem because it does not consider any actual truth value because given time point and interval, we have to have a fixed number of time point. Therefore, can generate unnecessary fine partition with unnecessary many time points. Okay, then how can you reduce that? So actually, here is some observation. So, okay, this picture is slightly a bit complex, but it's actually simple. So now I explain. So consider this formula, eventually I phi, and suppose that there's a sequence of interval, right? So point, open interval, point, open interval, and suppose that phi is true at this interval J6 to J8. Okay, then by some analysis proved in our paper that this formula is true, stably true in this interval. Okay, so basically, given the truth value of stable interval of subformula, we can obtain which part must be stable in the each temporality formula. It can be also defined for more complex formula like until or release and so on. So actually then now we can observe that instead of all the point, we can only consider rising and falling edges. Therefore, so rising edge means that whether is become first true, and falling edge means true to false. First true and true to false. And then by doing that, of course, we can ignore many redundant position. But of course, we have to keep track of actual truth value. But okay. So example is that suppose that this formula has a partition by this time point, and then suppose that the atomic proposition is stable for all these interval. But even though there's a many time points, 1, 2, 3, 4, 5, 6. There's 6 time points, but there's only one rising edge and the one falling edge. Therefore, you only need to consider 2. Therefore, the interval Q, partition Q would be just a P union, these 4 time points where 0 is all the same. Therefore, the size is minimally increased. Okay, so it's a very simple idea. Although it's simple, but actually formalizing involves some difficult steps though. But anyway, so we are now able to build a first order formula that define the constraint over SMT variable similarly by this fully stable refinement. And to give us some idea how it looks like, I shall show some snapshot. But you should not try to understand this, but just to give us some idea that in the encoding itself, we include that whether it's a going rising edge or falling edge, where rising edge, falling edge can be defined in a usual way, like that, true some value and negation at the next step. Okay, well, falling is similarly. So the rising and falling edge itself can be defined symbolically, and then we can encode the condition I mentioned symbolically as well. And therefore, finally, we can give this fully stable refinement condition as a SMT formula. Okay, right? So I just quickly skip that part because Anyway, therefore, we can reduce SMT encoding of satisfiability to just SMT satisfiability. So this formula means that first interval is the top position, right? Therefore, if the original the relationship formula is mentioned in the previous theorem, and then this is a fully stable refinement formula, and then correspond to one top position, satisfiable if and only if this phi is satisfied by signal is at most k variable points. So yeah, now the extra condition shown in previous theorem removed because this new fragment of formula represent that. Okay, by combining them, actually, we can have some SMT encoding of bounded STL water checking problem. So that by having some, as usual, encoding for negated formula, we can say that this negative formula is satisfiable if and only if, okay, encoding of negative formula is satisfiable if and only if the counterexample trajectory of phi at most k variable points and now also mode change. Because encoding of the system part require to have k mode change as well. Okay, so it's basically a conjunction of the typical encoding. I just briefly explain here. This is for system interval, system encoding, and the encoding I mentioned for relationship and also free stability. Okay, so by conjunction, taking conjunction of them all, we can obtain this encoding, and then this can provide encoding for reputation complete encoding for bounded STL Murray checking problem. Okay, now using that, you develop Murray checker. And before doing that, we also consider slightly simplified setting of this robustness. So basically, we want to Murray check, a robust Murray check up to some robustness threshold. That means for any numerical perturbation up to some threshold, the result should not be changed. That can be actually done very easily because for the first order logic theory, it's possible to numerical strengthening or numerical weakening of some first order logic formula, and then also similarly you can easily define numerical strengthening and numerical weakening of STL formula. That means a signal satisfies some strengthening if all of its numerical perturbation up to this threshold satisfy that. So this is just an extra layer. Okay, and then for algorithm level, you also perform some abstraction, but I just skipped it. It's no time. Anyway, this is now some architecture of Murray checker. So we're given hybrid automaton or hybrid system, and then two bounds. One is the discrete bounds and time bounds. And time bound can be infinite though, but for a special case. And then, as I mentioned, using the previous theorem, we can have an encoding of Boolean stem Murray checking. Then using this threshold, robustness threshold, we can epsilon strengthening this formula. Then by combining them, okay, now we have a SMT encoding of robust stem Murray checking. And then you can use typical SMT solver like G3S2 or DReal for ordinary differential equation. If there's a counterexample, it show counterexample, and otherwise, it's verified up to specific given bounds and robustness threshold. So, and then this can be reputationally complete by incrementing bounds. Okay, and then we can also implement the various optimization method previously known for hybrid system, including removing hybrid automata-based removing of image quantification and so on, not quantifier elimination. And then the tool is publicly available on this website. And then this is some demo somehow of the tool. We can provide some hybrid automaton format as usual, but using mode invariant condition, flow condition. Here is given by ordinary differential equation or jump condition. And the tool also recently also support other format like SpaceX format and so on. But this is close to D-rich format, SMT-based Murray checker. And then you can declare proposition and then declare STL goal. And then it provides some command line interface using various parameters like discrete bound or time bound or threshold, robustness threshold or solver or some optimization algorithm. And then it can either say no counterexample found or counter is found at a certain bound. Okay, and then if counterexample is found, then using satisfying assignment returned by SMT solver, we can draw counterexample. For example, this is for thermostat example. This visualize the drawing where this show trajectory of the proposition, and then this is the trajectory for each sub formula. Although I didn't mention that each sub formula itself may have some numerical value because of the no time, and then also it's quite technical. But anyway, this show the counterexample, and then using some experimental evaluation, we successfully perform for typical hybrid automata benchmark for quite complex nested STL formula. For example, for linear dynamics, where the continuous dynamics is a linear function, you can use S2 and then obtain this kind of result. And it's quite efficient somehow. And then for ordinary differential equation, here we use d-real. And the d-real itself is actually quite slow. So basically, it just kind of show that this can be done, but practically often not that useful. But anyway, using d-real solver, we could verify arbitrary complex ordinary differential equation. It's a involve nonlinear ordinary differential equation, and then can verify some complex STL formula and estimate up to some robustness. All right. Okay. Now, because it's time's up, I'll come to chair. So some summary. Basically, signal temporal logic has been proposed more than 20 years old, and they're widely used for analyzing cyber physical and hybrid system. But previously, it's more focused on deterministic signal. All right, so monitoring or falsification or model checking is quite limited to invariant and reachability property or their simple variation. And then our goal is to provide bounded model checking algorithm for general class of STL formula. And then there are to deal with some technical challenges, we consider syntactic separation and signal discretization technique. And then using that, we have developed the tool for robust STL model checking. As far as I understand, is the first tool because there's not many people worked on that. And it is reputation complete, and then able to verify many existing hybrid system benchmark. And then the future work, we are working on now how to do without SMT. It's basically automata-based STL model checking can be. How can you can perform automata-based STL model checking without SMT solving for general STL formula, and then so currently we consider bounded signal here. Bounded means finite number of variable points, right? Then how can you do that for unbounded signal? Could be done using some typical existing technique for various certificate and inductions, something like that. But how can do that for STL is also some question. All right, that's all for today. And then thank you for listening. And happy to answer any question.
So this is the beauty of these workshops, right? That we can also ask questions during talk, right? Maybe it's not, but of course also now. But thanks for asking in between and taking your time for that. But that's the point. We're having a small workshop. So it was serious. You still have some question.
Yes. Under what license is your tool available?
Open source license. So I don't remember exact license, but it's one of the open source, I think. Yeah. So what's that? I don't remember. Sorry. But it's open source.
The very standard question, so refutation complete means it guarantees that if there's a counterexample of length k, then it will find it.
Yeah, exactly.
But then the user needs to manage that they choose k properly. Right?
Or tool can continuously increment the bound.
Yeah, exactly.
Yeah, of course, but user cannot wait for arbitrarily long time. So practically there's some bound.
So this is the usual problem with bounded model checking. It's not really a problem because in many cases it's practical. I wonder whether you have some guidance on the diameter of a model, so that the user gets some guidance on what is the minimum k to be chosen, knowing some properties of the model.
Yeah, that's actually a good question. So actually, honestly, I have to say, even for invariant property, for a typical hybrid system, people do not much consider that kind of diameter problem because typically this model checking of hybrid system, two reasons. People typically consider very simple discrete dynamics involving only 2 or 3 states. So diameter there is visible by head, just by eye.
Yeah.
And then second one is that if number of jump increase, like that more than 100, something like that, even for very simple system, it's not feasible. Therefore, people typically focus on for bounded analysis. Yeah, although there's unbounded analysis that requires some manual intervention and they're very limited dynamics. But anyway, but for some general bounded analysis, the bound tend to be not aiming diameter completeness. Okay, all right, that's one thing. And then, as I mentioned, if the hybrid automata is very simple, then diameter can be just guessed by the longest path without cycle and so on.
Yeah.
But for STL, currently there's no such result, unless in this boundary.
Yeah.
But for the current work we are working on, based on automata based one, it's possible to provide some diameter because it related to generating some automata, and there you can have the same analysis by longest acyclic path and so on.
Yeah. Thank you very much. That's helpful.
Thank you. Yes.
I think we have to. Well, you'll be here for the whole day, so yeah. So just thank you. Well, there's nothing scientific. So thank you so much for doing it. So merci and merci in the French as well, right? So thank you so much for coming here. So
Thank you. Thank you so much.
hope you survived the trip.
Yeah, nice gift. Thank you. Yeah. Thanks so much.